years, 5 or 6. It's like Predator. I don't got time to bleed. I don't get time to be sick. All right, so it's week 7, and I'm gonna. Joe, you had a question about problem 2. I will answer that, but I want to catch up on anything I might have missed on the discussion board here. So let's do this. I'm not seeing the discussion board lighten up quite as much. I don't have to kick it off in this course, do I?
What's that?
It's not incumbent upon me to start the forum. It's just in my biofuels, I think.
Right.
Okay. All right, Joe, Ryan, and Schneider, energy to run the fridge. Let's see what you got here, Joe. There are an awful lot of different types of refrigerators out there. Anyone find a good place for average fridge use or have any idea what figure we should be using for problem 2? I'm about to start working. In the meantime, let's compare their answers. Let me know. Hey, so Dodie, let me just remind you, you're not supposed to post your Excel documents. In fact, I'm going to email Sean right now, just to remind him. It's okay posting PDFs, but not Excel documents in here.
Yeah, my problem is I create a PDF, but when I do an Excel sheet, it's more width-wise.
Yeah.
The PDF cuts everything in half, and I'm like, well, shit.
Well, another way to do it, I'll show you. Okay, close that down. Okay, and here's what, Joe, here's what I'm going to just suggest on this type of question. So there are an awful lot of types of refrigerators out there, but here's how to go about that type of problem. Rather than get overly concerned about the actual numbers you're going to use, just use something. Just get started with something. And here's another way to think about refrigerator energy consumption. So if we go to this guy, tools, pen, fine chisel, black, you're going to see 2 different types of wall outlet. And I can remember, is the big one on the left or the right? Yeah, the big one's on the left. Neutral. Yeah, neutral is on the left and hot is on the right. And what you're always going to see is the hot one is going to be your black, and it's smaller because it's harder to get your finger in there. That's the one that's going to shock you, right? And then your ground is down here. I didn't see, there were no ground wires in Japan either. Only 2 prongs.
Yeah, how do they do that? I
don't know. Okay, but this is going to be a 15 amp circuit, and then if you see this guy, again, it's going to be your black. Here's your 20 amp circuit. So, and all refrigerators are required by code to be on their own line. You don't put your fridge and your microwave and your toaster oven on the same line. So your fridge is going to be on one line. So the max power, max fridge power equals, let's just say 110 volts times 15 amps. 110 times 1.5 equals 1650 watts. 1650 watts. This is going to be a max for a 15 amp circuit. If you got a 20 amp circuit, max fridge power equals 110 volts times 20 amps equals 2200 watts. You're almost never going to see a fridge that powerful. Normally, they're going to run anywhere between 5 to 10 amps. I think the one in my house is like 7. So best thing to do is just get started with something. And as you probably noticed in this course, I mean, yeah, you do want to come up with the exact right answer. I mean, you do want to come up with a numerical answer, but most of your work is going into the modeling. You know, turning that word problem into some numerical model that then gives you a, so anyway, that's how I would approach that guy. About to start working, what's going to come with, let me know, duty cycle. Oh, here we go, nice. There you go, 4.5 amps, 115 volts. Nice.
I think I went to like an Energy Star webpage and just
found something.
There was like an average of 500 watts or roughly, you know, so that's what I just used.
Yeah, 500 watts sounds just about right. And while we're on that topic, and I think, yeah, 500 watts, 500 watts if you've got a 5 amp fridge, 500 watts equals about 1/2 of one home. So I think we've talked about this before, but one house is about 1 kilowatt. And this is pretty funny too. I won't name any names, but while I was in Japan, I had the opportunity to interact with some folks who, you know, actually deal with energy and power on a fairly regular basis, and I kept hearing that the copper mine in Butte uses 46 megawatts of energy a day. So, which is not correct because megawatts does not measure energy. Megawatts measures power. Yeah. So to get the amount of energy, and I gotta run this. So 46 megawatts times 24 hours. There we go. Let's just see what their energy bill might be. So 46 times 24 equals 1104 megawatt hours per day. So that's 104,000 kilowatt hours per day. So that's about $1,104 per day to run that they burn through in electricity.
Wonder how much of that is due to their water treatment facility for the
I think almost all of it. I think a lot of it's going into, because I think most of their machinery there is diesel powered, but yeah, I guess a lot of this is running pumps. Yeah. You know, which is a little ironic. So you're running your pumps, which are mainly burning coal to keep the water out of the keep the junky water out of the river, but you're sending CO2 anyway. Yeah, but so your fridge is not going to be running at full blast 24/7. Your fridge on average is going to run about 1/10 of your electricity bill. So that means that the duty cycle on a fridge is going to be right around 20%. Right, because 500 watts times 0.2 equals 100 watts, and 100 watts is about 1/10 of a house. So, on average, your fridge is sucking in about 1/10 of your power bill. Okay, based on the fact that it's only running about 1/5 of the time. Okay, yeah, let's get back. So thanks for that. Another thing, I told you I would grade every 3 weeks, and I am in fact a little bit behind, but that's what I'm going to do next here. I'm going to answer Joe's question, and then I might just do a little bit of in-class grading while you work. Then I'll get back and see what's getting missed here for 214. So let's hop back in. Joe had a question on week 7. So hopefully you guys are catching up on week 6 by now. Let's look at Learning Unit 7. In fact, this is kind of timely. I had a blackout in my neighborhood today. My roommates texted me, like, what's going on with the power? I said, well, I don't know. It's still on down here. And I'm just reading through this. Frequency is controlled to 1/100th of a hertz. The steeper the slope of the change, the faster the system needs to react. That makes sense. When load exceeds generation, frequency decreases, and the AGC signal is to increase generation. When generation exceeds load, frequency increases. That makes sense. And the AGC signal is to decrease generation. What is occurring on the graph below where the slope line is drawn? Right, so it looks like this guy got a little bit steeper than the other ones. This one seems to be 1 minute time 1/6 of a second. Frequency. Oh, I see. So the frequency is running just below 60. So it's like, hey, let's hurry up and get back up to 60. And the generation exceeds load. Yeah. So right there in that slope, the generation is exceeding the load. The generation is trying to get back. There's more generation than there is load, so the frequency just popped up. And then when it goes down, so it looks like here they overreacted, and so the thing is always oscillating. It's a pretty cool graph. I've never seen that before. That's on the order of 1 minute. And I bet if we dove in, we'd see even smaller fluctuations there. Very cool. Very cool. System operators fondly remember when the grid was simpler and the load was the main independent variable that changed. Wow, so it really is the frequencies changing. It varied in predictable patterns, and the only crisis periods were during storms and the unexpected loss of generation. Now, with the increase of intermediate renewable generations, so wind and solar, that is going to make it, and this is why that Tesla battery in your house is going to help fix this problem. It's going to balance the load. It's either going to be charging or discharging. Also, I just want to say this for record. I just finished reading Elon Musk's biography.
Yeah.
Unbelievable. Unfreaking believable what that guy's been able to pull off. It is mind-blowing. So if you get a chance, read that. I've been quoting him all day long. Okay, grid operators are looking for more tools to balance load and generation. The collective load, all customers together in like Missoula still have usage patterns that are mostly predictable. What variables do you think could be used by a system to predict tomorrow's energy use? Well, the weather. Think about how your pattern use may vary. I just turn everything off. I don't use it. One management tool is energy storage. So I just mentioned batteries. Another option on the load side is demand response, which sends signals to either automatically or manually increase customers' loads. Yeah, well, these smart meters. Smart meters are becoming quite controversial.
Oh, really?
Well, the smart meter is usually has a radio frequency associated with it, and some people are saying that a bunch of extra RF in the air is making them sick. So anyway, yeah, there's the whole TED Talks on it to send customers a variable price signal, also known as time of use rates. For example, and we don't worry about this much in Montana, Pacific Gas and Electric, during a critical pricing period, wow, 1 kilowatt hour is $1.50. Well, because if you go over it, you threaten to bring the grid down, you know. Also, there's some demand reduction, and utilities evaluate both the energy savings and demand reduction for conservation projects, and some have more demand reduction than other project. Less efficient lights will reduce demand. LEDs is a good example. In other words, a project for the people. Lastly, the peak load of the system is termed differently by generation staff. From a generation point of view, they use the term capacity. In other words, there should always be enough standby capacity. Right, all generators have a spinning reserve obligation. A few ways to accomplish this requirement include do not load your generator to maximum capacity. That makes sense. So if you're already running at max, so the idea there is if there are, let's just look at it this way. Let's just say I'm a power company, and I've got a couple, and I'm just going to draw a couple gas-fired turbine. That's my own acronym, by the way. Gas-fired turbine. Fine. Now let's just say this guy is 150 megawatts, and this guy is 150 megawatts. What he's saying there, and let's just look at a time of day graph here. So if this is midnight, this is noon, this is again midnight, here's 6 a.m., and here's 6 p.m. The curves, the residential curves tend to kind of go like this. You got the two humps. You got the two rush hours. There's the morning rush hours, and here's the evening rush hour. Dishwashers, fridges opening, garage doors opening, computers turning on, lights turning on, all that stuff. Now, if I'm a grid operator, and let's just say for the sake of argument, this is 400 megawatts. So I already told you that a house is a kilowatt. So this would be 4,000 houses. 400 megawatts, 4,000 houses. And you've got these two gas-fired turbines, each of which can do 150 megawatts. Well, and let's just say your peak is up here, and you know that you're probably never going to hit 400, so that these two have enough capacity to supply the demand. Well, but right around here is your 200 megawatts. So if you're an operator, by the time you hit 100, sorry, I'm kind of running out of space here, but if 100 is down here, and you know you're about to hit 150, let's just draw a little red line in there. If you're going to hit 150, let's just say 150 is here, 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 here. The question is, when do you kick on? So here's one turbine, and here's two turbines. The question is, when do you kick on two? Well, you're going to want to probably kick it on right here. And you might kick it off right here. And you might kick it on again here, and you might kick it off right here. So in these little green lines, you're going to have one turbine running, and over here, you're going to have two turbines running. You don't wait until this turbine one is already maxed out. You're going to have some headspace on it, 100 megawatts, 125. And what the text is saying here is that some of these generators can come up to speed much more quickly, and the gas-fired generators are much quicker to response than a nuclear power plant, for example. Man, there's so many bells and whistles. Oh my gosh, to get those things up and down. All right, so that's that. All right. Use both of the, read both of the thermal battery articles. Load shifting. I like that a lot. I'm going to take a peek at it just to. So yeah, I could definitely see. Well, if it was, that's the thing though. You'd have to have an electric water heater, which pretty expensive to heat water with electricity. I want to look at this stuff. Week ending. Dollars per short ton. Look at that. It's true. It's even worse than I thought. We sell our coal for $10 a ton.
Wow.
Why?
And it's anthracite too. It's like the best stuff, right?
This is bizarre. This is bizarre. This is just, I'm sorry, okay. I'll just say this right now. Shame on you, Montana capitalists. Capitalism is about competition, and this is not competition. That is giving away the bank. Tell me I'm wrong. Tell me I'm wrong. Why are we giving away our coal? I just don't get it, man. Why are we charging $50 a ton and giving that money back to the state? It's just baffling. Why would we give it away? Why aren't all those numbers right around the same?
Yeah.
That is bizarro.
Powder River Basin is like some of the best coal in the world, right?
I was just there. I just saw them digging it out 5 tons at a time. Giving it away, free.
They made $50.
Wow. Wow. That's shameful. I mean, I thought we had some responsible capitalists in this state, but maybe not. Wow. The BTU level is less than what we're seeing in these other places, but why would we just give it away? A quarter of the market price.
It's way lower than sodium dioxide.
Man. Whew.
There's just so much of it.
I guess so. Now, dollars per short ton. Western Rail, there we are, giving it away.
Yeah, that's on the bottom.
Yeah. Okay, so I used to give people some credit, but not anymore. Weird. That is weird. I had not seen that before just now. I hope someone can explain that to me. Okay, I'm still not sure how this is related to, let's just go back into the website. Okay, cost of coal, water heaters can support the load shift. So coal cannot be turned on and off. What I thought they were going to talk about was to just dump extra heat into hot water tanks. Okay, let's see what we got here. Okay, and the heat rate. Let's just remind ourselves with the heat rate. It's okay. So it's. And I always get it backwards. I know we covered this. We actually just covered this in bioenergy. Heat rate. So it's BTUs per kilowatt hour. Yeah. So it's BTUs of coal to make a kilowatt hour of electricity. So it is. Let's write that down. Tools, pen, chisel. Heat rate equals so it is. It's BTUs per kilowatt hour. So this equals in over out. So heat rate equals 1 over efficiency, because efficiency equals out over in. Okay, that's why it's always confusing, but I want to clear that air. Okay, let's go back. Let's go back. Okay, so these are all pretty straightforward. Other factors about coal. Okay, it's still not clear to me what's going on with the storage here. Let's just keep reading. What is the assumption for this shortcut factor? Oh, let's see what the shortcut factor is. How does it differ from using the 70% for problem LED? What was LED problem? What number was that?
That's number 2.
And this week?
Yeah.
Okay. Let's see what the shortcut answer is. I'm not sure what shortcut he's talking about.
I was a little confused on what he was getting at there.
Well, I think this is pretty obvious though. So if you're going to make a kilowatt hour of electricity, so if you're going to run your house for one kilowatt at a kilowatt, which is normal for an hour, you're going to need to burn 1 pound of coal. Or you're going to need to burn 1/100th of 1,000 cubic feet, or 10 cubic feet of natural gas, 10 cubic feet. Or you're going to have to burn 0.07 of a gallon. So, tenth of, right around a cup of oil to run the house. Kilowatt hours produced, so this many kilowatt hours per ton, this many kilowatt hours per MCF. Assumptions. Well, what we're looking at is that there's some average BTUs per kilowatt for coal, some average for gas, some average for petroleum. I'm not seeing anything about losses here. So maybe the answer is that there are no losses, because there are losses all along the way. There's thermal losses of the plant, there's losses in the lines, so maybe that's all the answer he's looking for, is that the losses are the same across all systems. I don't know. Okay, let's keep that in mind. 70% for problem with the LED. Okay, at Electric Power Research Institute, I talked with a person from Sacramento Municipal Utility District about an energy storage project using compressed air. SMUD owns a wind farm in an underground cavern. They also have the mineral rights, so they own the cavern. Since the profile of wind generation is mostly at night, so the wind's blowing at night, this seems like a perfect match to store wind energy while the prices are low and sell the stored energy when the prices are higher. This is an arbitrage value of energy storage. Okay, right. So non-peak, so this is the, so $50. So did you say you made a little progress on this one?
Yeah, I think I got it done.
Okay.
I didn't get the extra credit yet, but
okay.
Main problem done.
Okay. All right. Well, if you want to share that, that would be great. So I'll let you guys chew on problem 1. Let's look at problem 2. Okay. Imagine you're working for a municipal, customer-owned nonprofit, electric utilities and energy analyst. Your utility is vertically integrated, meaning it owns the generation, transmission, and distribution. Nice. To deliver electricity to your customers. Your boss wants you to report on the elected Board of Commissioners about a residential conservation problem. Okay. So you want to get the spreadsheet for your analysis. Great. Little written document. Cool. Prepare an outline strategy for your audience. You can create a presentation if you need extra points for this class. It may just be a little PowerPoint. I mean, really all it would just be a PowerPoint that has a snapshot, a clean, nice snapshot of your spreadsheet, probably some graph that people can read easier than a table. Right. We can read, we're making tables in Excel all the time. And then, take the one page and turn it into some bullet points. Okay. Answer the following question.
Are we actually going to summarize the program?
Let's just see. I'm going to work through it in real time here. Let's just see. If you were doing a presentation, what other presentation materials would you need to prepare? Okay, your utility owns a coal power plant. Fine. 10,000 incandescent bulbs were replaced in your customer home and businesses for a program cost of $500,000. The same number of bulbs was removed and installed. Okay, so 100 came out, or 10,000 came out, and 10,000 went in. 75 watt were replaced with 18 watt bulbs. The LED bulbs had an occupancy sensor. Okay, super. Use the power plant T&D system losses from Lovin's article. This should look familiar to the motor belt fan. You'll need PP and T&D losses for this problem, since the rest of the office and aim resistance illustration are on one of the customer's side of the meter. We can assume. So coal's the primary. Average operating hours are 3,000 per year. The occupancy, take it down by 25%. Estimated carbon tax, ooh, nasty, $5 a megawatt hour is assumed to be assessed. Your customers pay 8 cents, discount rate, 8-year life. Nice. How much energy was lost at each stage of the process, considering generation, transmission, and distribution. Include the power plant. The scope is problems. How much do save annually? Provide the units. How much did the program cost? Utility. Okay. Don't worry. Lost revenue. Okay, don't worry about this. From less energy sales, or the efficiency of the coal, the effect of your customers' HVAC. Yeah, that's funny because you turn the lights on in the winter and it heats your house, so don't worry about that. Accounting for the difference in light bulb life. Okay, that's good. That's good. I mean, the LEDs are actually going to save you much more time over the long run. Are you wow. Knocks, socks, and rocks. That's a good one. That's the first one I've heard. Okay. And then what else is in here? That's it. Okay. Have you started the spreadsheet yet, Joe?
I just got some of the given data down.
Okay. Let me start in on it. I don't mind doing some of this, and I am not going to write much down on my my pad here, but what I do suggest you all do, well, maybe I will. What the heck? I'll write it down. I'll write it down. Okay. So we've got 10,000 incandescent being replaced with 10,000 LEDs. Good. We got 75 watts over here, and we got, what did it say, 18 watts over here. All right. And then these are going to be on 100% of the time, and these are going to be on 75% of the time, if I've read that correctly. Coal is the input fuel. We're looking at 3,000 hours per year. That's true for both. 3,000 hours per year. Carbon tax. $5 per megawatt hour. So let's get that on a new page. Per megawatt hour. Guys, I saw this thing. I still can't believe it. I'm sorry. I have to go back. Where was that? Sick.
Nicole?
Yeah. I am sorry. That's just dumb. You know what makes it even look even dumber? Is that. Like seriously, can someone explain that to me? Okay, that's enough. That's enough. Problem 2. Wow. Problem 2. customers pay 8 cents per kilowatt hour. And we're looking at 6% discount rate, 8-year life. So I equals 0.06, N equals 8. All right, and I think I've been going for a while now. Yeah, I'm going to take a break, and we'll get back and solve it.